Hey everyone, and welcome. Today, we're going to do something really cool. We are taking a super powerful, pre-trained model and turning it into a specialist that can identify almost 200 different types of cars. We'll be using the legendary InceptionV3 architecture and a technique called fine-tuning to get some seriously impressive results. Let's dive right in.
So you've been there, right? You spend hours and hours training a model. On your training data, it's getting incredible scores. It looks like a genius. But then you show it a new image, something from the real world, and it just completely falls apart. Sound familiar? It's a classic and super frustrating problem in machine learning. This huge gap between how it performs on data it's seen versus data it hasn't, that's called overfitting. Your model has basically just memorized the answers to the test instead of actually learning the subject. So it looks brilliant in training, but it can't apply what it learned to new situations. Our whole mission today is to build a model that actually understands cars.
To pull this off, our secret weapon is a two-part strategy. First, we're going to stand on the shoulders of giants by using the powerful InceptionV3 model. And second, we're going to use a sophisticated two-phase training plan that goes way beyond basic transfer learning to get us some really robust results.
So here's the game plan. Phase 1 is what we call transfer learning. We're going to take that pre-trained InceptionV3 model, freeze all of its layers so they don't change, and then just train a brand new custom classifier on top. Then for phase 2, this is the fun part, we'll carefully unfreeze some of those deeper layers and fine-tune them with a tiny, tiny learning rate. This two-step dance is the secret sauce.
But before we can even think about building a model, we need to get our fuel ready, and that's the data. We're using the Stanford Cars dataset, and let me tell you, getting it prepped for a model like InceptionV3, well, it has some very specific rules we need to follow.
Okay, rule number 1, when you're working with a pre-trained model like InceptionV3, you have to respect its input format. Every single image needs to be resized to exactly 299 by 299 pixels. This isn't just a suggestion, folks. It's a hard requirement for the architecture. We'll also process our images in batches of 32, which is just a good, efficient way to train. Now, to stop our model from just memorizing the training images, we use a clever trick called augmentation. We're going to use a Keras tool that creates slightly different versions of each image as we train. It'll rotate them, zoom in a bit, shift them around. This forces the model to learn the real features of a car, not just one specific photo. And, this is critical, we leave our validation data completely clean, untouched, so we can get a true, honest measure of how well it's actually learning.
All right, our data is prepped and ready to go. Now it's time for phase 1, transfer learning. The plan is beautifully simple. Load up the pre-trained InceptionV3 model, lock down all of its existing layers, and then bolt our own custom-built classifier right on top.
This new custom head is where all our specialized learning is going to happen. We start by pooling the features from Inception to simplify things. Then a couple of dense layers get to work learning the complex patterns. We sprinkle in some batch normalization to keep the training process stable and fast. And then we've got dropout. Think of it like a teacher who randomly covers up parts of the textbook. It forces the student, our model, to learn more robustly and not just rely on one thing. Finally, the output layer gives us the probability for each of our 196 car classes.
So, before we train our new piece of the model, let's get a baseline. If we just take the raw InceptionV3 model and ask it to identify these cars, how well does it do? Brace yourselves, a dismal 0.37% accuracy. It basically has no idea, it's just guessing. This is our starting line. To make sure our training is as efficient as possible, we're going to use a few automated helpers called callbacks. Early stopping will stop us from wasting time if the model hits a wall and isn't improving. Reduce LR on plateau will help it get unstuck from tricky spots. And model checkpoint, that's our safety net. It automatically saves the best version of the model as we go. And after that first phase of training is done, look at that jump from less than 0.5% all the way up to 56.4% accuracy. That is the incredible power of transfer learning right there. Just by training that small custom head, we've turned a generic image model into a pretty decent car classifier. But hey, we're not done yet. 56% is good, but we can do better. It's time to move to phase 2, fine-tuning. Now we're going to get surgical. We're going to carefully unfreeze some of the deeper layers of InceptionV3 and teach them the specific details of our car images.
The key to fine-tuning is to be gentle. We are not retraining the entire model from scratch. We're only unfreezing the top layers, in our case, the last 23, which handle the more abstract, complex features. Then we recompile the model with an absolutely tiny learning rate. This is so important. We just want to nudge the existing weights in the right direction, not accidentally erase all the valuable knowledge they already have.
And the result of all that careful work? We squeezed out another percentage point, hitting a final validation accuracy of 57.3%. Now, I know that might not seem like a giant leap, but in the real world, that small improvement is often the difference maker. It's that final coat of polish that takes a model from good to great.
Okay, we have officially gone through the entire process, so let's just take a second to step back and really appreciate the journey our model has been on, from being a complete novice to a real car recognition expert. This timeline just puts everything into perspective, doesn't it? We started at pretty much zero. Transfer learning gave us that massive, game-changing leap in performance, and then fine-tuning came in and provided that final incremental boost that got us over the finish line.
But all of this is on our validation data. The real test, the ultimate test for any model, is how it handles a completely new image from out in the wild, one it has never, ever laid eyes on before. So, let's give it a try.
We fed the model an image it had never encountered, a 2007 Hyundai Elantra, and as you can see from these results, it absolutely nailed it. The top prediction is correct, and with super high confidence, almost 80%. The other guesses aren't even in the same ballpark. This right here is the definitive proof that our two-phase strategy really worked. This table really tells the whole story. But look at that top 3 accuracy. That is especially impressive. It jumped from about 1% to over 77%. That means for any given image, there's a 77% chance the correct car is in our model's top 3 guesses. That just highlights how incredibly effective this whole strategy was.
So we've walked through the entire workflow, from getting the data ready all the way to a final high-performing model. The big takeaway here is that transfer learning does most of the heavy lifting, and then fine-tuning comes in to add that last layer of expert polish. And now, it's your turn.
If you want to try this yourself, or maybe adapt this process for your own project, I've put everything you need in one easy place. You can get the full commented code and a detailed step-by-step written tutorial over at dataskillblog.com. Go check it out.
And that brings us to the end. You now have a powerful, repeatable workflow for building highly accurate image classifiers. So my question to you is, what are you going to build first? Thanks for watching.